In this lecture 7, we will see how to calculate the deformations under axial load. Here we can see a BC segment of initial length L and a cross-sectional area of A, and due to this P load which is stretching this BC segment, del amount of change in length occurs, and by the definition of strain, so we can express that strain is equals to change in length divided by initial length, and we know that stress is equals to force per unit area. That means force P, which is acting here, divided by cross-sectional area A. And we had also learned the Hooke's law in our previous lecture, which expresses the relation between stress and strain up to the elastic limit. So according to Hooke's law, stress is equals to strain into modulus of elasticity. Now combining these three equations, that means from strain changing the side, we can write change in length del is equals to simply strain into initial length, and from here changing the side, we can write strain is equals to stress divided by modulus of elasticity, or Young's modulus. So now combining those equations, from this equation we can see, right here, plugging the value of strain, that means sigma by modulus of elasticity here, and then again plugging the value of stress, which is P by A. If we combine all those equations, we will get this new relation, which is change in length is equals to PL by cross-sectional area into Young's modulus, or modulus of elasticity, E. So this change in length simply expresses the amount of deformation in that particular section. So let's see a problem regarding this. In this problem, we are asked to determine the deformation of the steel rod AD, shown at left. Shown here, the given loads are 30 kips, 45 kips and 75 kips, and we can see this AD steel rod is fixed at one end and this end is free. So we can easily conclude that there are three segments in this rod. First one is this AB segment, and second one is this BC segment, and third one is this CD segment. So accordingly, here we can see that there are three loads acting, and these three loads are mainly axial loads. We know from the internal force lecture we had already learned that there are three types of force. One is axial force, another one is shear force, and another type is bending moment. Here we can see only the axial loads, and in this lecture we will calculate the deformation due to the axial loads only. So we can see here three axial loads and three segments. The first axial load is 30 kips, second one is 45 kips, and the third one is 75 kips. Now as this end is free, so we can easily see the, or we can easily consider the condition, which is the effect of 30 kips will be acting throughout this third segment, which is CD, and the combined effect of 30 and 45 kips will be acting on this CB segment or BC segment, and the combined effect of these three forces, or the net forces due to this three load, which is 30 kips, 45 kips and 75 kips, the combined effect of these three loads will be acting on this AB segment. this AB segment. So now taking the sections, we will be able to calculate the deformation as firstly the net forces and as well as the deformations. Let's see how we will be able to solve this problem. So firstly, taking a section at CD, anywhere in between CD, we can see there is only a single load in this CD segment, which is 30 kips. This 45 kip starts just at the left of CD segment. So taking a section in between CD, we have taken a section. Here we can see 30 kips. According to the law of equilibrium, we know in order to keep this section in an equilibrium state, a similar force will be acting in opposite direction to keep this section at equilibrium state. So we are expressing this opposite reaction or opposite force with P3, and we can easily see here that the value of P3 will be 30, but using this equation of equilibriums like summation of f of x equals to 0, we can calculate the P3's value also. So here the value of P3 will be 30 kips. So the effect of 30 kip, that means the net force of 30 kip is acting on this CD segment, and the length of CD is given here as 16 inch. And now we can see this 45 kip load just after this CD portion. So now we'll have to consider both the effect of 45 and 30. So taking a section in between BC segment, so we have taken a section in between BC segment. As we can see, in this BC segment, we will be able to get the combined effect of this 45 and 30 kip load. So we have considered this 45 and 30 kip load here. Now for this 45 and 30 kips, for this 45 and 30 kips, we can see the net force will be 30 minus 45, which is minus 15. So the net force will be minus 15. So here is the net force, minus 15. As we know, according to the law of equilibrium, same amount of force will be acting on opposite direction in order to keep this beam in equilibrium state. So we have considered a load here P2. So the value of P2 will be minus 15. We can calculate this value of P2 using the equations of equilibrium also. So if we use the equation of equilibrium, summation of f of x equals to 0, here we can see minus P2 minus 45, as 45 is acting in left direction and 30 in right direction, so plus 30. From here we'll get the value of minus 15. So the net force is minus 15. We will see the effect of minus 15 in this BC segment, where the length of BC segment is 12 inch. Now after BC segment, we can see the introduction of another load, which is 75 kips. So for AB segment, we will need to consider the combined effects of 75, 45 and 30. So taking a section in between AB segment, so we have taken a section in between AB segment. So now we need to consider the three loads and calculate the net forces. So the net force will be 30 minus 45 plus 75, in total 60. So this 60 kip load will be acting in opposite direction. So here we have given the opposite direction. We have denoted it with P1. So we can easily calculate the value of P1 using the equation of equilibrium, which is summation of f of x. So using the summation of f of x, we can see the value of P1 as 60 kip. So the net force 60 kip, the effect of this net force will be acting on AB segment, where the length of AB segment is 12 inch. So we already know the net forces acting on each segment. the length of each segment and also the cross-sectional area of the segments. Now from our previous slide we had already seen that deformation is simply equals to load, which is the net load or the net force P, initial length or the length of the segment L, divided by cross-sectional area into modulus of elasticity. So we have already calculated the net forces for each of the segments. We have calculated the length of the segments are given, the area of the segment is given, and the modulus of elasticity. From our question we can see that the material is steel, so the modulus of elasticity of steel will be 29,000 ksi kip per square inch. So plugging all those values and summing those up for each of the segments, summing all the deformations of segments, we will be able to calculate the total deformation. So total deformation will be simply equals to summation of the deformation in all segments. So deformation for each segment will be PL by AE. So we can see here 3 segments, and for these 3 segments the material is same, so we have taken the 1 by E as the common one, and considering it outside of the bracket, now we'll be calculating the deformation for each of the segment and then summing those up. So for segment CD, the value of net force is 30 kip, and we have considered it as P3. So we are just plugging the value of P3 here. We are just plugging the value of P3 here as 30. The length where we can see the effect of P3 is in CD segment. The length of CD segment is 16 inch, so plugging the value of L3 as 16, and the area of CD segment is 0.3 inches square, so plugging the cross-sectional area, and then in P2, while considering this net effect minus 15 kip, this net force will be acting on BC segment. So the length of BC segment is 12 inch, plugging the value of BC segment 12 inch, the net force minus 15, and the cross-sectional area 0.9, we will get the deformation of BC segment. And similarly for CD naught, it will be AB, it will be AB mainly, the third segment, which is AB segment, this AB segment. Here we can see the length of AB segment is 12 inch, so plugging the length here, the net combined force acting on this AB segment is 60 kip, plugging the load and the cross-sectional area as well, we will be able to calculate the total deformation. So summing those all deformation in each of the segments, we will get the total deformation as 0.076 inch.